I don't know. The recording is going on and off. Now it has started. Okay, good. Fine. So 10th lecture, now we are starting with induction motor in the course Advanced Electric Drives, and some basic things first we will understand about induction motor, what its torque speed characteristic is saying, what its equivalent circuit is saying, what approximations you can take, when it is valid. All these things we will discuss, and then finally we will be ready with going ahead with the starting of the motor, and then why do we need inverter or any other thing to operate the induction motor, what are the problems. Okay, so I think most of you are very much aware about what is induction motor, right? There is nothing much to say. Some of the qualities we also know that it is very rugged, very robust and reliable, sparkless. So all these qualities are there, all these properties are there. So DC motor, if we see, we have let's say the field present on the stator, you can say, and the armature is rotating. So we have certain current direction given to the coil. Now what happens? Let's say this north and south pole, this kind of arrangement is there. So for a particular direction of current, this field can apply torque only in one direction. So let's say if this is in this direction, north to south, and the current is going inside, so how the torque will be? In which side? Can you tell? Either it will be left or right, right? Which one it would be?
Right, sir.
So torque is coming over here, or this actually the opposite direction, torque will come in this direction, right? So basically not torque, I should write at force. So then it becomes torque when it's on the rotating body. So now what happens when the force or this thing is applied, it rotates, and then this positive direction of current comes near the south pole. So then the force will be reversed because the direction of current is reversed. Now in order to maintain the rotation direction, we need to maintain this force as well, which means the current in these coils need to be changed whenever they reach on the opposite poles. So that is where the commutator and all these things, brushes and all these things are used. They flip the direction of current whenever it reaches to the other pole direction. Okay, so this is some kind of arrangement, commutator, brush and all that is needed to do, and that's why there is a spark and all these things over there. Now here we are dealing with static magnetic field, right? And that's the problem. So this is overcome when we talk about induction motor. We have naturally rotating magnetic field. So we have, instead of DC supply, here we have AC and of course three-phase supply, and then on top of that this is distributed in space. When I say three-phase balanced RYB, this is somehow distributed in time. So when you distribute the windings in space as well, we can generate a flux which is, let's say, rotating in one particular direction. You understand this point? This basic thing we know, right? So quickly we can see what is happening. So we know that, let's say, if there is any coil, say I draw the dot and cross, which means the coil is perpendicular to the paper or this whiteboard what you are seeing. So this is the direction where the coil is going. Of course the motor is cylindrical, right? So one conductor is going like that, and then it is returning over here, and that is how this current is flowing. This is going in, this is coming out. Now if this is the kind of coil which I am talking about, how it will generate the flux? So right hand thumb rule and all these things you can see, and then this will be the direction of flux along the paper. This is all what I have drawn slant lines. These are all perpendicular to the paper. So on the paper what you are seeing over here, or on the whiteboard what you are seeing over here, if this is going inward, this is coming out, the flux direction will be on this paper towards the right hand side. This is all on the 2D. Correct? This point is clear, right?
Yes,
Now
sir.
let's say we are feeding a current, let's say some IR equal to some Im sine omega t. And because this is sine omega t, so definitely the flux generated by this, say phi r, will be some magnitude phi m sine omega t. Correct? So what will happen with time? How the flux will vary? Your current is changing something like this, and flux is also changing something like this, maybe a different magnitude you can say. Correct? So what is happening actually with the flux magnitude, if you see, so basically whatever projection you see on this y-axis, that is the value of flux what you are seeing as magnitude over here. So sine omega t maximum could be 1, minimum it could be -1, and the value is varying between this. So is the flux value varying between minus phi m to plus phi m. And you can visualize that as the projection on this y-axis. Correct? So in effect, what is happening whenever you are feeding this sinusoidal current to this coil, sometimes you have flux which is, let's say, when omega t equal to 0, the flux is 0. When you have omega t equal to 90 degree, you have maximum flux. When you have again omega t equal to 180, again it comes back to 0. Then at 270, it goes to maximum negative, and then it comes back to 0. So any intermediate value it can take only along this axis. You understand the point? So depending on what is the value of omega t, this flux can take value on this axis, whether some positive value maximum going up to phi m or some negative value maximum going up to minus phi m. This is clear, right? There is no confusion in this. Now this is the property which any sinusoidal or this variable kind of flux is having. Now when we have, let's say, time distributed coils or time distributed supply, you can say, we have phi r generated by some current which is coming something like this sine omega t. We have phi y coming as some phi m sine omega t minus 120, and we have phi b coming as some phi m sine omega t plus 120. So what is happening? These all quantities will take the maximum and minimum values at different theta. For example, at theta equal to 0 degree, phi r would be 0. Phi y would be some minus phi m root 3 by 2. Phi b would be some root 3 by 2 times of phi m. Isn't it? This point is clear, right? That is what the nature of this time distribution is. So this is taking different value at different time. Now, if you take another point, say 90 degree, so what will happen? Phi r would be maximum phi m. Then phi y would be something like minus phi m by 2, and phi b would be something like minus phi m by 2. The important thing to notice over here is that the algebraic sum of all these three is 0. Always. And that is what we say balanced. So at any theta you can check. Similarly, all this will have different value. Where the algebraic sum, let's say phi r plus phi y plus phi b is coming as 0. This is happening on account of the time distribution. Now we are going to introduce another aspect in this when we are making a motor, which is called space distribution. And then what we have, I may need to take help of some drawing tools. So just let me check. Okay, nothing, no. Just a second. I don't know, somewhere, okay, here it is having this, yeah, into shape. Okay, so I think it will make, correct. Good. So because it is important to have at least some nearby clear shapes. So now what I'm going to do on this circular stator, that I'm going to keep the coils in a space distribution manner. Say R, I'm drawing with this red color over here. Correct? And I'm going to distribute Y and B with respect to R at 120-degree locations in this space. Okay, time it is already there. So let me mark these angles properly. So some of the advantages and some of the disadvantages with online teaching. Okay, maybe once we mark, then this will be good enough to utilize it again and again. Okay, so roughly something like this is coming over there. I think center is little bit messed up. Okay, now what we are going to do basically, we are going to place our Y and B coils as well. So this is say plus R over here and minus R. So I told, right, it's a cylindrical machine. So coil showing this dot is basically the current is coming out and then this is going inside. So we have Y, then it will come over here, but we have to keep in mind that we are distributing in space such that we get a, so Y I will draw with green. So something like say 120 here. So this is plus Y and this is minus Y. And then what we have is B. So which is plus B over here and minus B over here. So notice that the direction I am going is R is here and then Y is lagging on this side. Now, generally, when we draw something like this, we have Y coming over here and this, right? So the difference between the space and time distribution is this. When you draw on time, basically this phasor is rotating. Whereas here the coil is not rotating, the coil is fixed. The flux generated by this Y will in effect create that resultant which will be rotating in the counterclockwise direction for balanced RYB supply. Now this is what we are going to keep for our next few illustrations, let us say. Okay, now what we have, let us say one by one we can just try a few instances. Let's say at theta equal to 0 degree, what is happening. So we have seen that phi r is having 0 value, phi y is having some minus phi m root 3 by 2 and phi b is having plus pi m root 3 by 2 value. Now, where is that going to be placed in this coil? So R is certainly 0 over here. B is along this thing, along the negative y axis and minus phi m root 3 by 2. So This is the positive y-axis. So along this it is going to come. And then we have phi b, which is going to come along this. This is the positive b axis. Correct. You again use the right hand thumb rule. So you would know where the thumb is pointing, that is the positive direction, and where the opposite side is, that is negative axis. Now we see the resultant of these two is coming along this. Isn't it? This is clear, right? So at theta equal to 0, the resultant flux is coming somewhere, say resultant I indicate by phi s. But because of space distribution, this is not algebraically added, but it is vectorially added. And so this phi s is coming something like the value of 3 by 2 phi m. Correct, right? Any problem in that? Fine. Now we
Yes,
go
sir.
to next instance, theta at 90 degree. What happens? Phi r is now at plus phi m, whereas phi y and phi b both are at minus phi m by 2. So what will happen now? Let me draw next instance in red. So we have r coming as maximum, say phi m over here. Then we have y coming along the negative and b also coming along the negative. So for y this is the negative, so it is coming here. And for b this is the negative, so it is coming over here. Axis you need to mark very clearly for this illustration. Now when again you add these points, minus phi m by 2 and phi m by 2, minus phi m by 2 again. So vectorially again if you add, this comes back to 3 phi m by 2 magnitude for the phi s. But it has shifted from here to here. It has rotated from this position to this position. Any intermediate angle if you want to check, say 30 degrees, 60 degree, you can do on your own. You will see that it is gradually shifting from here to here. You understanding my point? Correct, right? For example, one more intermediate angle, let us say we take theta equal to some 120 degree. Now our phi r would be some phi m root 3 by 2 and phi b would be minus phi m root 3 by 2 with phi y going equal to 0 at 120 degree, right? So what we have, let me draw in black, phi y is 0. And then r is having a value something like root 3 by 2 times of phi m. And b is having a value which is minus phi m by phi m times of root 3 by 2. Because I am drawing on the negative axis, so I am not writing minus. Okay. So either on the axis or by magnitude, you have to somehow indicate that the quantity is going negative. So now some of these two will come along this y-axis and the magnitude will still be 3 by 2 times of phi m. And it has rotated from here to here. You understand the point? So this is how we are able to generate the rotating flux by having the space distribution. This is very preliminary thing, you all know, but still just to illustrate and to understand how this is happening, this is a good way to enhance your understanding. Correct? So likewise, you can go for any other angle and you will see that it is going in the counterclockwise direction for this balanced RYB. If you keep RBY reversed sequence, then it will become clockwise. You can try that on your own, right? Good. Now, this is one property about induction motor. The other thing what you already know, but still let us just have a discussion on that, which is equivalent circuit. Because most of the computations what we are going to do for PWM and other things that will be based on equivalent circuit, we need to understand this very well. So we know that for squirrel cage induction motor, we have the equivalent circuit given as this, right? The quantities also you know very well. Yeah, so can you tell what is RS? Quickly. RS is
Starter resistance.
stator resistance. XLS is
Starter inductance.
no.
Reactance.
This we call
Leakage
as
reactance.
Leakage.
yes. Stator leakage reactance. Now this is not inductance. This is not L. This is X. So stator leakage reactance. Similarly, we have rotor leakage reactance, magnetizing reactance, and then we have the rotor resistance, which is basically scaled by 1 by S, where S is this slip. So we know S is nothing but the rotor frequency divided by the stator frequency. And rotor frequency is nothing but omega synchronous minus omega m divided by omega S. So in effect, what we have basically omega m coming as some 1 minus s times, sorry, 1 minus s times of omega s. Correct? This is some primary definitions which we know already. Now, we also know just a quick recap of its phasor diagram. So this we will revisit again when we are discussing the harmonic torque. So only for your information or reference, I am keeping it here, but I will revisit this when I am doing the harmonic torque analysis in much more detailed way. So we have, say, let me indicate it like E1, and then we have the IR. So IR into RR by S, and this J XLR IR. Some same IR is coming over here. We have some IM, and then these two are forming the I1 or IS, you can say. Now this E1 is projected on the other side. So why this is projected on the other side? Why it's not similar way? So these discussions we will have in more elaborate manner. What is the meaning of when we are putting it from here to here, whereas it is same thing on the equivalent circuit. So all these detailed discussions we will have. ISRS and JISXLS, and this is what is V1. Just for your reference, okay, we will have all very detailed analysis later on. Now, today's focus would be more on this equivalent circuit and going for the torque speed characteristics from this, and then seeing the effect of rotor resistance insertion. Now, what we have basically, this is the equivalent circuit of induction motor when we are talking about the exact equivalent circuit, right? Steady state per phase equivalent circuit. Now we can take some approximation what you must have done in your previous classes, that this magnetizing reactance can be taken at the supply end, and then the rest of the circuit can be connected like this. Now the question is, yes, we know that this is possible, but when is it valid and when is it not valid? When you can say that yes, this approximation holds very good, and under what condition do you say that no, this is not a very good approximation? Yes.
So when magnetizing current is value is very less as compared to the load current value.
Okay. Then whether it is valid or not valid?
Sir, error is there, but it is very small.
No, but what is the conclusion? Say IM is very small compared to IS. This is what you are saying, right?
Yes, sir.
So under this condition, is it valid or not valid? That's what the question is. Okay, I'll give you a chance to think a little bit more about it. But if we talk about the approximation validity in general, no, when we have induction motors, there may be different power levels, right? So if I categorize three power levels, let's say low power motor. So this is, I'm something talking about say 5 horsepower or something like that. Then there may be some category of mid power range. So this is something like 25 HP or something like that, no, 25, 30, or maybe you can go up to 100 HP, something like that. And then the high power motors, where I am talking about specifically power levels going above 500 kilowatt. So if these three categories we have and we try to see which circuit is giving better result, or at least if this approximation is coming close to what is actual or not. So two examples I have plotted over here for your reference. So is this visible to you?
Yes, sir.
Okay. So this first motor, what you see over here, this is kind of, from the torque level itself, you can see 100 Newton meter. So that's a small power level motor, right? Now, this is what is our actual. The black one is showing the actual characteristic. The red one is showing the approximated characteristic. So what we see that yes, there is lot of difference when we talk about in terms of the torque level, maximum torque generated, and no, for the higher slip operations. But for the low slip operations, actually where the motor operates, this approximation is still good. Slip value could be like 2%, 5%, which is this range, this is small range. There, these two characteristics are very close. So whenever you are doing any computation, even for a small power motor, the actual power, the actual torque, the highest torque or the peak torque, what is happening, that may be different. That may be little far from what you are getting from the approximate circuit. But if the analysis is done for the low slip operations, this is still valid. You understand the point? Another important point to notice over here is the point or the slip where the maximum torque is occurring. This is not changed, only the value has changed. So the nature of characteristic is more or less same. You understand the point? And we will see slowly why is that happening, how it is happening. Now, another example I give for high power motor. You see how the torque is going up to some 20,000 Newton meter. Okay, now here these two characteristics have come very, very close, even up to a little more or little higher slip value. Even the peak torques are not very far. This is something like 19,360 and this is 17,824. So if you check in terms of percentage, these values are not very far. Understanding my point? So for higher motors, the approximation results into much better values, and for lower power motors, we have definitely very good approximation for the low slip operations. So when we proceed with this, we know that this approximate circuit is giving us lot of advantages because the computation becomes very simple. So we need to know that where we can apply the approximation and where we cannot. You understood this point? Now we are going to use this approximate circle to come up with the torque slip characteristic and all these things. Okay, so one common mistake which actually many places people have done is that whenever they start computing from the approximate circuit, they simply take RR by S and XLR alone for the computation purpose. So many a times they come up with maximum slip torque as some RR by XLR. Okay, if you see some common places, you will find this mistake. This happens only because not only we are ignoring the parallel reactance, but also we are ignoring this stator impedance in compared to the rotor, which is not true actually. Okay, so let us see how this is going to come and what we can get out of it. So we have XLR RR by S. Now if we have to write the rotor current, so basically rotor and stator currents are approximately equal. So from here you can write the IR as V1 divided by this RS plus RR by S square and XLS plus XLR square. This is common thing, there is no problem. Now without any trouble, we can take the approximation that RS plus RR by S is very close to RR by S. There is no problem at all in this approximation. Okay, because the value of RR by S is very large. And here what we can say, because for most of the common motors we see this property, leakage reactance for the rotor and stator are almost equal. So then this expression for IR can be written as V1 divided by RR by S whole square plus say 4 XLR square. This point is clear, right? Now I am going to introduce a term called as alpha, which is nothing but the ratio of rotor resistance and rotor leakage reactance. This is a very common term which just by seeing the machine you can say that okay, this is what this alpha is, and then you can guess lot of things about the torque speed characteristic of the motor. So we will make it like that. Now IR is coming out to be, if we rearrange this thing in alpha and S, all these things, so it will come out like SV1 divided by XLR 4S square plus alpha square. Fine, XLR you have taken common, S has come out. So then this is the rearrangement. Fine, this term is clear to all of you? Clear, right?
Yes, sir.
Good. Now we all know when we have the rotor current, we can write the mechanical power output, or okay, mechanical power output we can write, and this is nothing but 3R square RR 1 minus S by S. So rotor loss we have ignored, and then whatever remaining is basically our power. And then we know that torque can be written as PM, the mechanical power divided by the mechanical speed. There is no doubt in that. It's very clear thing. So the rotor speed we can write as, now small p I am writing for number of poles. Omega is 1 minus S. Correct? So according to the pole and slip, we can write the mechanical speed in terms of this. Correct, right? Now this we are going to use to come up with the torque speed characteristic. Okay. So tau is now 3 IR square RR, and 1 by S cancels out. So we have, and one more term is there, which is okay, we can write later on P by 2. So then we have S omega S times of P by 2. Correct? This is correct, right? Nothing is missed out. Then we can rearrange and we can bring down the value of IR from this expression. So what will happen? 3P by 2 we can take out here. Then we have 1 by S omega S say here. And then we have IR square. So S square V1 square divided by XLR square times of 4S square plus alpha square. And then we have RR. All the terms are there, right? Nothing we have missed out. Fine. Now, if we rearrange this again, and again we can use this alpha factor over here. So what will come out? this S will cancel here and one XLR will come out, V square will come out. So V1 square divided by XLR we can take over here. Omega S also we can take over here. And then what will be remaining with is basically S times of alpha divided by 4S square plus alpha square. Is that fine? All the things are there?
Yes, sir.
Correct. Now what you can do basically, because all these quantities on this 3p by 2 v1 square omega s XLR, this is all constant for a given machine. So we can mark this as some kt. So this can be written as kt times of s alpha by 4s square plus alpha square. Now we are going to have the torque slip characteristic for the induction motor on basis of this expression. Again, see, something which you can visualize, something which you can draw easily, understand easily is much more appreciated. You can plot the exact curve for this, but to understand what this is, you need to break this again similar to our asymptotic body plot. So what are the approximations that we can take? Torque can be written in two forms. Let's say when S is very small compared to alpha, or say alpha by 2 for some reason I am keeping. Okay, when S is very insignificant compared to alpha by 2. So what will be the expression over here? The 4s square will be ignored with respect to alpha square. So we will have kt times of s alpha by alpha square, which is effectively nothing but kt times of s by alpha. No problem in that. And this is the case we are saying that when s is very less than alpha. Now another case I take when s is very large compared to alpha by 2. So alpha normally for any motor, if you see big motor, something like reasonable power level 100 kilowatt and so, this is something like a ratio which is equal to 0.2. This is the typical number you will find for any reasonable power motor. So then S can be much more than alpha by 2, right? There could be some range, say 0.8, 0.9, all these are very large. So then this alpha square will be insignificant compared to 4s square, and this can come as S alpha by 4s square, which is basically kt times of alpha by 4s. Correct? We have two separate characteristics for two different ranges. One is simple line. It is only proportional to S. Another is a curve, hyperbolic curve, which is inversely proportional to S. Clear distinction we have, right? Now, what about these two curves? Where do they meet, these two approximations? So you can say kts by alpha equal to kt alpha by 4s. At this S, these both curves will meet. So if you compute, this will come out to be plus minus alpha by 2. At this point, these two curves, the line and this hyperbola will meet. Clear? That will be the intersection point of these two curves. Now, let us draw how it is coming based on our experience or based on our expression. So again, I need to use a scale because at least some level of accuracy should be there. And this is not confined to only motoring mode or only one particular mode of operation. This is like we are having complete range of operation for the motor. Okay, let us say here we have S equal to 1. So this is 0, 1, and then it is extending beyond 1. And then similarly we have something like minus 1 over here, which corresponds to the generating mode. This is all motoring mode up to 1, and then the other mode of operation, whatever is there. And then torque is here. So we know that for both the expressions at S by 2, when we are saying S equal to alpha by 2, the value is coming out to be kt by 2 for the torque. Isn't it? That is the point or that is the value this torque is taking at s equal to plus minus alpha by 2. So we can mark these 2 points as well. Say somewhere here is our kt by 2. Correct? Now we have, let's say, alpha by 2, which will be approximately 0.1 coming over here, and then alpha by 2 something like coming over here minus. So then for this section, this value is kt by 2 minus kt by 2. So for this section within minus alpha by 2 to plus alpha by 2, this is behaving like a straight line, and the value is going from this minus kt by 2 to plus kt by 2. So we can have the line joining these points. Say this characteristic will extend something like this. The other characteristic what you are having is basically a hyperbola, which is again meeting at kt by 2 at this point. And if you check at s equal to 1, the value will be something like kt by something like alpha is say 0.1, sorry 0.2. So this is something like 0.05 times of kt. Correct? From here you check. This is what it is coming. So if this is 50% of kt, this is 5% of kt. Somewhere here, let us say. Okay, so this hyperbola will continue something like this. These are two curves which are defining the operation of motor for different ranges of slip. The actual characteristic is basically very, very close to these curves, and it goes something like this. Pardon the drawing inaccuracies. And this will hit this maximum value somewhere here at alpha by 2. That is what this is suggesting. Now the different modes what we are getting for the induction motor is like 3 different modes of operation we are getting over here. Whenever the slip is between 0 and 1, this is basically the motoring mode. And this is where we say that our rotor speed is less than synchronous speed. Then whenever we cross 1, basically this is the plugging operation. Plugging means suddenly you have reversed the terminals. So your omega r becomes negative with respect to the synchronous speed. So this slip has gone more than 1. And then the slip negative is basically the generating mode, and which is where we have omega r greater than omega s. Correct? Now, can you forget the torque speed characteristic of induction motor ever? So something which we can visualize and something which we can feel that, okay, this is going to be of this kind of characteristic, where it is going to meet, where it is going to have maximum. Now this is what the characteristic is saying, that the maximum value of torque is nothing but kt by 2, and the value at which it will maximize is this. Correct? So if you want to prove the same thing from the expression also, you can do that. Let's say you don't approximate, simply have this. And you try to get the maximum torque. So basically d tau by ds should be 0. So what this will come out to be? Kt alpha divided by 4s square plus alpha square minus S alpha times of 8s divided by 4s square plus alpha square whole square going equal to 0. So simple differentiation I have taken. Now what this will do? So KT and the common factors I will remove. Then the remaining thing will be 4s square plus alpha square minus 8s square going to 0. And basically alpha, or we can write S, is nothing but alpha square by 2. S square is alpha square by 4 and S is nothing but plus minus alpha by 2. So yes, slip can be positive, slip can be negative, and then we have the 2 points where the torque can be maximum. You understand the point? Correct? Now, to see the validity of this point, what we are having, let us say, we know that if you go by the elaborate equivalent circuit, Thevenin's equivalent circuit and all that, you will come up with the expression for this S max T, something like this. Isn't it? This is the expression which we know, right? Generally for the maximum slip. Now, what we have basically Req and Xeq is basically the parallel connection of the magnetizing reactance and the stator impedance, XLS. So if you connect these two in parallel, effectively you will have this lower impedance only coming out. So RS plus JXLS parallel with XM is more or less parallel with JXM is more or less RS plus JXLS. Isn't it? Now what we are getting over here, R2 or RR, let's be consistent little bit with that. So RS square plus XLS plus XLR whole square. Now again, if you see, the stator resistance is coming in combination with the reactances, stator plus leakage reactances. And in most of the cases, this component is dominant compared to the stator resistance. So again, we can approximate this as square, and which is nothing but what we have said. Sorry, this becomes 2. So which is basically alpha by 2, our factor. So even with the accurate expression and all these things, we are not very far. You understand the point? You understand the point?
Yes.
The approximations are valid even with the most accurate expression. Which is what this curve is also saying. See, despite taking the approximation, why these points are matching, that's the reason. Approximately 245 or 24 something, no, this is what the curve is coming as. And for high power motor also, we are having these 2 points almost close. Maybe here it is little far, but this is somewhat broken. So you can say here or somewhere there. No, it's not very far. Understanding my point? So you can check with practical examples. Still, with this analysis, you can quickly tell that how much maximum torque you are going to get and what is the slip at which you are going to get the maximum torque. Fine. So when you are given the parameters, you should not take time to compute all the elaborate terms to just get to know where all these quantities and how these quantities are going to occur. You can straight away tell that, okay, this is where I am going to get approximately my peak torque, and this is going to be the value of the peak torque, Kt by 2. Fine. Now, with this, we can also understand the impact of adding some rotor resistance. Let's say we are talking about the wound rotor motor, where we have the provision to attach some rotor resistance to the motor. How the characteristic is going to change and what is the maximum value up to which we are going to have any advantage of this. So what we have basically the torque expression coming as some kT s alpha by 4s square plus alpha square. This is what the expression is. And we are seeing that the maximum torque is occurring at this. Now alpha is nothing but effective rotor resistance divided by the rotor reactance. Now let us say we are inserting some resistance in the rotor. So the effective resistance RR dash becomes something like this, where R external is the external resistance. So obviously when you have some extra resistance inserted, the value of alpha will increase. And so the slip at which the maximum torque is occurring will also increase. Say I am talking about only motoring mode. So this will increase with alpha. In effect, what it will look like, if this is your maximum value and we are talking about only motoring mode, let us say, so we have kT by 2 over here and the characteristic is going maximum at say this alpha by 2 and then there is some other alpha where some rotor resistance is inserted, then it is increasing to other value. So several characteristics we will have based on the external resistance. And then falling. Fine. Now what we say that if we write say resistance R external is 0 over here. This is the natural characteristic what motor is having. Then some R1 is inserted, R2 is inserted, R3, R4 and R5. So we know that R5 is having the highest value. Anything inserted beyond this point R5 will actually not give you good starting torque because it will match here. At starting you will basically lose some value. So there is a limit on how much resistance you can insert for practical reasons. It will be disadvantageous if you insert any resistance more than this R5 value. Now what is this maximum value that you can compute again from the same characteristic that S max T is alpha by 2 and maximum value for this could be 1. For slip could be 1 where the maximum torque is occurring. So alpha max could be 2, not more than this. So then what we have basically is R external coming out to be 2XLR minus RR. This is the maximum value of resistance what you can insert in the system for getting the most advantage. After that, this becomes disadvantageous. You are basically improving the starting torque with every insertion, right? So this does not keep increasing forever. There is a limit, it increases and then it falls down if you keep increasing the R external. Understanding my point?
Yes, sir.
Good. Some feeling you have got about this?
Yes, sir.
Good. So I stop over here now, and we have got the basic understanding about the torque speed characteristic and how the starting torque is changing with resistance, what is happening. All this we have got. Now tomorrow we will discuss little more thing about the starting of the induction motor and going towards the need for inverter or the methods to have smooth start. Fine.
Sir, tomorrow is holiday, right?
Not tomorrow, yeah, Thursday.
Oh, okay.
Yeah. Tomorrow means next class, whenever it occurs. So by default, you take this as the meaning. Okay. So any doubts, any confusion you can ask now up to this point.